Hello, fellow chemists. Jolly here. This discussion is going to be on bond and molecular polarity. Now, there's a few things that are very important that you have solid before you try and figure out polarity. Number one, you've got to be able to draw those Lewis structures. And I'm not talking just any Lewis structure. I need the best Lewis structure. You have got to be able to figure out the shape of that molecule. And then 3, you're going to have to remember your electronegativities. So if you struggle with this at all, kind of review whichever of those pieces that you need to. All right, bond and molecular polarity. Let's define polarity first. Polarity is basically a difference in a charge or a separation in a charge. So separation of charge. Another way to look at it is it will line up in an electric field. Alright, so basically polarity is there's a difference. There's one side that's either true positive and true negative, or there's a partial positive, partial negative, but there is a separation of charge. Now, you can have 2 kinds of polarity or dipole moment, okay? A dipole is basically the sides of the charges. Okay, and that sounded really lame, but you kind of get where I'm going there. So it's basically a quantitative measurement of the degree of the charge of the separation. Okay, and I guess that's probably better anyway. The degree of the charge. Let me see, degree of the charge separation. So a dipole means there is a separation, and then you can have really big dipoles, or you can have smaller dipoles, depending on how far apart those are, or the magnitude, if you will. All right, there is an overall net dipole. A net or a permanent dipole means it is always there. Permanent. I spelled that wrong. I know it doesn't really matter, but it would drive me nuts. There's a net or a permanent dipole, which means overall the charge stays or exists. Okay? And net, just like in money quantities, you would talk about having a net loss or a net gain. Okay? So an overall, what is the final charge? Now we can also have an instantaneous dipole. An instantaneous dipole, it does not exist at all times. It's a temporary dipole. Due to the movement of the electrons. All right, so polarity is the separation of charge. The measurement of the polarity is called a dipole. If it's permanent, we would call it a net or a permanent dipole. And if it only is there just for a moment because of shifting of electrons, we would call it an instantaneous dipole. Okay, there's our definitions. I liked that I said that. This is, if you will, the measurement. And those are the types. Okay, the best way to try this is to jump right in. So we're going to figure out whether something is polar or not. And the first question to ask is 1, Is there a polar bond? Now, what do I mean by a polar bond? Remember, a polar bond has two atoms, two or more atoms. Now, I'm just going to say two for right now. Let's simplify. Ran out of room. All right, is there a polar bond? Basically, I'm asking, are there two atoms bound together, and do they have different electronegativities? And just a real brief review, if you're looking at the periodic table, fluorine is the absolute most electronegative, and so as you get closer to electronegative fluorine, you become more electronegative. The second most electronegative element on the periodic table is oxygen, and then nitrogen and chlorine are kind of tied for third place. So the closer you are to fluorine, okay, so is there a polar bond? And if you want to know the magnitude, we need to know basically how far apart are they. Or basically, how polar is the bond? The bigger the difference, in electronegativity, the more polar the bond. So two things far apart on the periodic table will have a more polar bond than two things that are very close. For example, in a previous lecture, I talked about carbon being bound with hydrogen. They have two different electronegativities, so technically it's polar, but in the organic world, we think they're so close together that, well, sometimes we call it a nonpolar bond. But if there is a difference, we would call it polar, okay, if there's a difference. All right, so is there a polar bond? And if yes, how far apart is the polarity, or the difference in the electronegativity? Well, can you now come up with an overall net value? Okay, now this one is, we can do the math, but this one is the key. It is the absolute key. So it is based on vector math. And remember, in vector math, both the magnitude and direction matter. If you don't remember how to do vector math, it's okay. We're just going to do it visually, but it comes from the mathematical equations. Let's just take an example, and I'll show you what I mean. Let's take water. So we've got water. All right, number one, are there any polar bonds? And the answer is yes, because technically those are both polar, okay? Well, how far apart are they? Now, we can put a quantitative or a qualitative. These are fairly close together on the periodic table, or they're far apart, depending on how you're looking at the periodic table. But yes, they are polar. Well, can you tell me about how they're poling, if you will, their vectors? And this is called a dipole arrow. So I know that oxygen is more electronegative, so I'm going to draw the arrow pointing that way. So this side is more positive than this one. That's not a true positive and a negative. It's just poling that direction. Well, this one is pulling in this direction. I have to figure out, in the end, what is my overall net vector or my net dipole, and then draw an overall. So now if we were going to be doing vector math, what we would do is we would take this one and we would take this one, as long as you drew them correctly, and you would add them together and so forth and so on. I'm not going to do the math. We're just going to visualize. So my overall net dipole would be going somewhere that direction, which makes perfect sense because the lone pairs are more electronegative than either of these two bonds, and so I prefer to write it this way. It just looks a little cleaner to me. This symbol, delta, means partial, okay? So I have a partial positive here, and I have a partial negative up here, and a partial negative up here, and a partial positive there. And if I overall look at the whole thing, my overall, I would have a partial negative up there and a partial positive down there. Either way you draw, it's absolutely fine. But that is talking about the polarity of those bonds. And in this case, I also talked about the polarity of the molecule. I have a polar bond and I have a polar bond, and we're going to look at the net result to ask the last question. Is there a net dipole? If the answer is yes, then your molecule is polar. If the answer is no, it is not polar. All right, so how did I answer that question here? Do I have a polar bond? Yes. Do I have a polar bond? Yes. How do they, if you will, add together, or mathematically, how do they get together? There was a net dipole, so this molecule is polar. So that molecule is polar. Basically, you're looking for symmetry. Okay, that's another way of looking at it. Let's try a few more. All right, let's take a look at this one. You have to be able to draw those Lewis structures. All right, so this one is called methane. This is natural gas. How many things are around it? 4. What family does it live in? Tetrahedral. All right, are there any polar bonds? Now remember, you are not in an organic class. Yes, organic students, you would say, that's not really polar. In a Gen Chem class, is there a difference in electronegativity? Technically, yes, but not by much. Not by much. So I can either say, ooh, you're partially positive and you're partially negative. So you would put the negative on the one that has the higher electronegativity. And you are partial negative, partial positive. You are partial negative, partial positive. And you are partial positive, partial negative. All right, so are there polar bonds? The answer is yes. And I'm going to put a little asterisk because I know the organic chemists are groaning at me. And I am an organic chemist, so I do understand. Okay, so polar bonds, absolute yes. But do they have an overall net dipole? That's what I'm interested in. And the answer is no. So this molecule is non-polar. Okay, now there's 2 ways to look at this. This carbon, if you were to do all the vector math, the vectors would cancel. So basically, they are all pulling equally but opposite. I did not say 180 degrees. Equally but opposite. It's 109.5 degrees, but there's nobody that's winning. Okay, so that's one way of looking at it. The second way of looking at it is symmetry. Is the entire thing symmetrical? If the answer is yes, it is normally nonpolar? If the answer is no, it's normally polar. So that's one way to look at it. And then here's a jolly way to look at it. Look at the bubble. Do you see that the outside is a complete bubble of hydrogens? If the bubble is identical, there's no differences whatsoever, then that is nonpolar. All right, you're going to laugh. This one's called the jolly stupid rule. It lovingly got its name a long time ago. Even though I don't like to use the word stupid, it has stuck. For families, 2, 3, and 4. What we're going to say is, are all the things the same? If the answer is yes, it is nonpolar. If the answer is no, it is polar. End of statement. For family 5 and 6, I'm changing it just a little bit. Are all the things in the same location? The same. Yes, that piece is nonpolar. No, that piece is polar. And then you have to add the two locations together. So if you have a non and a non, you're overall non. But if you have a non and a polar, you're polar. And again, you're going, wow, jolly, jolly. Yeah, do it in words that I can understand. Okay, let's try it. We want to know overall, is the molecule polar? Alright, let's just put a whole bunch of molecules. I was doing methane. Alright, let's use the jolly stupid rule. How many things are around carbon? 4. Are they all the same? Yes. So therefore it is non-polar. Because I basically have a bubble of hydrogens that's hiding my carbon. So nothing can see the carbon because it's surrounded by a bubble of hydrogen, which is all the same. Let's try this one. How many things are around it? 4. Are they all the same? No. Therefore, it's polar. Why? Because we can now put our net dipole, this one's more electronegative, this side is going to be more electropositive, or we could draw an arrow kind of like this. There's an overall net dipole. Huh, is it really that simple? Yes, it is. I'm going to trick you. It is drawn flat for convenience only. Don't forget that. Alright, how many things are around it? 4. Are they all the same? No. Therefore, it is polar. Jolly, wait. These look like they're 180 degrees apart from each other. So therefore, they must cancel out. No. Remember, it's drawn flat for convenience only. Those are not 180 degrees apart. Those are 109.5 degrees apart. I should have drawn it like this. Or I could have put the 3 dimensions in it. Okay, so don't let that fool you. It's drawn flat for convenience only. Well, what about 3 things? What about 3? Oh, and I'm running out of room here. We'll just put it right here. How many things are around it? 4. Are they all the same? No. So therefore it is polar. How about this one? things are around it? 4. Are they all the same? Yes. So therefore it is nonpolar. Therefore it is nonpolar. And so that's the way you can do family 2, family 3, and family 4. Well, let's do family 5 and family 6. Now remember, you have to do the locations on these. So we're going to draw phosphorus here. Cl, 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 and a Cl. Now notice, even without drawing the 3 dimensions, your eyes are seeing it that way. And again, a proper Lewis structure does include all the lone pairs. If you do not see this in 3 dimensions, to determine polarity, you kind of have to. If you then you can just always draw these dashes and wedges in there if you want. All right, how many things are around the phosphorus? 5. Are they all the same? Stop. There are 2 locations. So I'm going to ask at the axes and the skirt. Are the 2 things at the axes the same? Yes. So therefore the axis, or the axis, is nonpolar. The skirt? Yes. So therefore it's nonpolar. And then you add those together, or that's a bad word. You compare them together and they're both non, so the overall molecule is non. What about this one? Alright. There's 5 things around it. Are they all the same? Look at the axes. The axes is no. So this one is polar. Because these 2 are different from each other. What about in the skirt? Yes. So it's nonpolar. But overall, a polar and a nonpolar, the overall polar wins. What if I drew it like this? Do you see why you have to look at the locations? Hey, are all things the same? No. Normally, if it was up through family 4, you would just say polar, but watch this. Are they the same? Well, the axes, oh, yes. So it's nonpolar. The skirt, yes, it's nonpolar. So overall, you still get non. That's the reason you have to look at both locations. All right. Oh, you know what? We need to do another one. Let's do P, F, F, Cl, Cl, F. Does it matter where they're located? And the answer is absolutely. If I had put this fluorine down here, that would look like this, and that would have been nonpolar. These are called isomers of each other. But it's not, because these 3 are in the skirt. But those 2 are in the plane. So just because it has the same formula as the one next to it, it's all about the location. So the axes is they are the same. So it's non. But the skirt, they are not the same. So it's polar. So overall, it is polar. Right, and these are called isomers of each other. It's the same formula, but they're connected differently, specifically constitutional isomers from each other. And that is the way you would figure out polarities for family 5 and for family 6. Whoa, is family 6, is there a trick there? We're just going to do one of them. Oh, I don't know, let's do SF6, I guess. Okay, going to get really sloppy, not going to draw in my lone pairs. Alright, this is family 6. Are they all the same? Yes. So if they're all the same, this one is non-polar. Because it's symmetrical, it has, if you will, the same bubble. of fluorines, or both locations are nonpolar. However you need to visualize it for yourself, it's all saying the same thing. What about this one? Notice the difference? These are non-polar, but the skirt right here, the skirt is polar because there's a difference. What about this one? Gonna trick you again. These are nonpolar because they're the same. Oh ho ho! Look, look, look! These are different, but do you see they're 180 degrees apart from each other? So they're canceling each other out. So it's nonpolar too. So for an overall non. And then we really haven't been playing with those arrows, but could you tell me how polar this bond is? Well, fluorine's the most electronegative element. So obviously it's going to pull harder than the sulfur, and that's how you would draw the arrow. Or you could say partial negative, partial positive. All right, that is how you determine the polarity of both bonds and for molecules. And that was seriously exciting. I know you're all groaning, but that is exciting in my world. So until next time, jolly out.